Good morning. We're going to talk about matter and how we read an element box from the periodic table. So here's the bad science joke. It can be anything and it makes up everything, but it always has space and it has mass. What is it? Well, if you look by the start of this set of notes, you'll probably figure out that it's matter. Matter makes up everything and has mass. So here's the official definition. Matter is anything that has mass and takes up space. Who knew? It basically makes up everything in the universe. It makes up you, it makes up me, it makes up this computer, it makes up the desk you're sitting at, or the chair you're sitting on, or wherever you happen to be. It's all made up of matter. So properties of matter. Each specific substance has its own set of properties and combination of properties that can be used to identify it. In class, we would take this box and I'd hand it out, and as a group, we would go through and sort it, and I'd say, okay, sort everything in here. And you know what everyone always forgets to sort is the plastic box. It's plastic. So how would you define plastic compared to a piece of wood, or this block, or this eraser? Well, I could say these are all straight lines. But these two are made of wood, where this is made out of rubber. These two are rectangles. These two have close to the same color tone. But then I could call this a rectangle too, but it's a sponge. Is that the same characteristics? How about this cork? Or this plastic bear? Hey, I could maybe put the plastic bear with the plastic lid. They're both plastic. I could say this is blue, and I could say this ruler, which is made out of plastic, is purple. I could say if it's folded, it makes a longer rectangle than if it's, folded up. Now it's a smaller rectangle, but hey, this is plastic too, so they can be characterized together. This is a rock. What characteristics would this have compared to, say, this bottle of water? These are the questions we have to ask. What do we know for characteristics of this? How would we sort them? And everyone sorts them in a slightly different way, and that's the cool thing, because some people will do naturally occurring. Rock can be considered naturally occurring, or organic, or man-made plastic. All of these different ways are fine to sort and organize matter. So when we look at that, my plastic box is one of those, we have to realize that there are different properties, and the properties are what gives its unique characteristic. The property of a plastic bottle isn't the same as a glass. A glass can shatter, plastic bottles tend not to. So there are physical properties, that is, the qualities of the material that can be detected by our five senses, or a measurement device. So physical properties of matter, for example, would be volume, mass, buoyancy, does it float? Conductivity, does it have electrons flow through it? Does it conduct electricity? Viscosity, how thick it flows. Melting points, boiling points, freezing points, the states of matter. Is it a solid, liquid, gas, or plasma? What is its size, its shape, its weight, or mass? Because remember, weight and mass is the same everywhere in the universe, but weight is dependent on gravity. So our weight, remember, on the moon is different than our weight here. So we like mass in science better. Density, that is its mass compared to its volume, its length. All of these different things are physical properties, like color, crystal shape, streak, magnetism, reflectivity index, luster, ductility can be pulled into a fine wire, hardness, malleability. These are all physical properties down here that we talked about in 8th grade, if you happen to have been here with Mr. Cater or myself. So the next thing we would do is look at that box, which we've already done. So properties of matter can be physical or chemical. So chemical properties are characteristic behaviors of a substance. So in other words, is it combustible? Does it react with acids? Does it burn? These are all chemical properties of matter, versus physical, which is a descriptor more. If we look at this is going to be chemical reactions. And this one we really don't need to have the sound, so I'm not going to bother putting it on. But this is getting into states of matter. It went from a solid to a liquid. If it vaporized, it would be going into a gas. And that is going from a solid to a gas. It's the boiling point. Ductility, can it be pulled into a wire? It's a property of matter. Helium balloons float. Well, argon balloons are denser gas and they actually sink. Sodium chloride is salt, and iron, different characteristics. I can actually separate the iron out from the salt using a magnet. We've got some salt crystals there versus some calcium for bone. Lead is a malleable metal. It can be moved. Ductility is, can it be pulled into a wire? So copper is great at being pulled into a wire. It's very ductile. And then we can shape things into different shapes. You also have reflectivity. In other words, how much light is going to be reflected back off of that surface. Calcite has the ability to refract light when we look for it. It's a very set pattern, so it's angular. And if we take some chemicals and put them in, get a chemical reaction, we can have in this case, it's an exothermic reaction. It's releasing heat and gas. So it's becoming something else. In fact, it's boiling. Put a little bit of that substance in. I think it's magnesium is what he had. And this is reacting with it, but it is actually going to burn up the steel wool. It's so hot. Sodium chloride will actually burst into flames with water. It can. The farther down you go, you can have that happen. If you mix a little vinegar and baking soda, you get an endothermic reaction. You get a reaction, but it's actually pulling heat into it. So if it pulls heat into it, it's cold. Exothermic reactions release heat, so they're hot. Fireworks are an exothermic reaction. Putting a little chemical together, you actually get something called a precipitate, which is you've got two liquids and you get a solid from it. Matches are a chemical reaction. And we're done with that one. Here is another one. If you wish to go and watch it, go ahead. Hydrogen peroxide mixes with potassium iodine. Actually, we'll watch it because this is super cool. These are all the cool, fun experiments. Sulfur hexafluoride is much denser than air. So in other words, you can scoop it out and pour it in and make stuff sink. And it's really, that aluminum is floating on the hexafluoride. And it is really dense. Super cooled water freezes on contact with ice. There you go. Liquid nitrogen and ping pong balls. Please do not try this at home. Please, you really can't get liquid nitrogen at home, so don't. And there, she's about to blow. There we go. There's a reason why you don't do this at home, but how cool is that reaction? These are all chemical reactions. Iron reacts with copper sulfate. Rust. Magnetic putty swallowing a metal cube whole. In other words, the magnetic force pulls it in. A gallium spoon melts in hot water. Looks like a real spoon, but it's not a spoon you want to eat with, because put in a little hot water and let's see what's about to happen. Boom, it's a liquid. Ferrofluid in a glass bottle, basically iron. Ferro is iron. Setting fire to lithium. Again, don't do this at home. Well, you can't get lithium, so I'm not worried about it. But it is a cool reaction. Iodine clock reaction. Sodium sorry, missed it. Basically, you're making snow. Well, not real snow, but chemical snow. Ferrofluid. Again, iron filings. They're magnetizing those cones, and the iron climbs up it, forming a pine tree-like shape. Flammable fluid in a gas jar. Again, don't try this at home. You can see the gas is burning all the way down. Smoke from a candle is set on fire. This is doable at home, but be careful and have your permission from your parent. Blow it out, put a lighter right above it. The gases ignite, relighting the flame. Water is deflected, so there's a charge to the water. So we're going to have a stream of water coming down. They get a static charge built up, and it's a little hard to see. It's better here, but we can actually see the water is attracted to the charge because water molecules have a slightly positive side and a slightly negative side. We'll talk about that later. It's called the Mickey Mouse. Fireworks exploding in slow motion, definite chemical reaction. Yep, there we go. That's definitely an exothermic reaction. It is giving off heat. Luminol reacts with oxygen. How cool is that? Okay, we're back. Sulfuric acid and, okay. Carnation frozen liquid nitrogen hit with a hammer. It's going to shatter because that is one solid. This is cool. Okay. All right, so basically all matter is built by elements, compounds, and mixtures. So we need to understand the difference, and this of course would be on the test. An element, for example, is oxygen, hydrogen, helium, carbon, potassium, sodium. It is a single type of atom, where a compound has two or more atoms bonded together. They're chemically bonded together. Sodium chloride. Take a little bit of sodium, really explosive metal, a little bit of chlorine, a poisonous gas, have them react together, and you get table salt. Water is always 2 parts of hydrogen to 1 part of oxygen. These are bonded together, either in ionic or covalent bonds, which we'll learn about a little later. And compounds then are basically 2 or more elements joined together, and they're always in a specific ratio. H2O and H2O is water, but if you have H2O2, you do not want to drink it because it's hydrogen peroxide. There's a whole bunch of formulas we could go through, but I'm not going to go through those until we get into formulas. A mixture then would be like air, milk, salad dressing. If you take a vinaigrette dressing, you have to shake it up to make it mix together, and then it separates out by usually density. Air has nitrogen and oxygen and carbon dioxide and water vapor. All of these things we can separate out. Your salad is a mixture of different ingredients. Take a cake mix, you can put them together, but as soon as you bake it, they've gone through a chemical reaction, you get something else. So an element is 1 type of atom. A compound is 2 or more atoms, types of atoms bonded together. And a mixture is just a bunch of different things. It could be an element, it could be or compounds, or any of that stuff all in one spot. So like your soil in your backyard. At the lake, we have a lot of sand, but at my house, it's all clay soil. Very different mixtures. So there's 118 elements that we know of so far. Elements can't be broken down any smaller and still be the same material. Now we can break an atom down smaller into the protons, neutrons, electrons, and we can break that down even farther. But if I break it down beyond the atom, doesn't have the same set of characteristics. So all matter is made of elements, and all elements have specific sets of property. So, by the way, these are atoms, and they can do some funky things with little teeny tiny atoms. It's still really, really hard to see inside of it, but we're getting closer and closer. I mean, when I was your age, we did not have this technology to see even this, but these are individual atoms. So the next thing that we would do in class, if we were doing this in class and you weren't watching it through that, is I'd actually give you a dime and have you, and you could do this at home or you could do this in class if you wanted, but I think we'll just talk it through. If you take a dime and you trace it onto a piece of paper, and let's say that that's the nucleus of the atom, and if we were in school, let's put it in perspective, we were in my classroom, I want you to think for a minute, how far, if the nucleus was the size of the dime, how far out would the electron cloud be? Is it You know, another dime. Is it a foot? Is it the width of the table? Is it the classroom? How far out do you think it is? Think about that for a second. If the nucleus of the atom is the size of a dime, how far out would the electron cloud go? What do you think? How far would you have to go? Well, used to be PDQ, and I can't remember what it is now, but that gas station on your way into Mound, that's about how far out your electron cloud would be. In all directions. Remember, it's not just to PDQ or up and down and around and all over. It's a sphere. And the one thing we know about electrons is the second we know where it is, we know it's not there anymore, because there is no real pattern. Although there is a pattern of how close they can get to the nucleus, and energy can be released if you force them up or down, but that's kind of like nuclear reactions, so we'll talk about that a little later. But atoms are so tiny, and the bulk of their substance is in the nucleus, but the bulk of their space is taken up by the electron cloud, which has hardly any mass at all. So a long time ago, we had all these different ways of coming up with what we thought an atom was, and you know, Democritus, he said that it's atomnos, Greek for unbreakable or uncuttable. It can't be made any smaller. And all those years, people tried to kind of poke around at the atoms. They'd look at bigger samples to figure out the characteristics, and they realized that if you have a big pure sample of gold, an individual atom of gold should have the same characteristics as the bigger chunk together. So, but they still couldn't see it. It's kind of like showing you that picture of the atom. They couldn't, I didn't see that. So it would be like taking this box, and I could use some of my senses, but you know, if I were giving you this box, I would tell you, please don't look through the hole, so you can't use sight. Please don't lick the box, because it's not going to help you out, so you can't use taste. But you can use sound. I can tell there's something in here. You could use this stick and try and use the little peepholes and see if you could find it in here, and try and speculate if there's some kind of shape. And maybe it's rectangular or maybe it's round. But that was as close as we could get to figuring out what something looked like, until we get these really powerful microscopes where we can actually start to see the atom. But up until then, we were kind of just coming at it with a blinder on, for a lack of a better term. And so if we were doing this in class and you were trying to figure it out, then you'd have to make a guess as what you think is in here. And I am that mean teacher, and I have never in 20 plus years let a kid open these boxes to find out what was actually in the box, because that was the point. There's a lot of things that happen in science that some scientists, even like Stephen Hawking, he never found out everything he wanted to figure out. But maybe someone in 10 years or 2 years or 100 years will figure out what he was trying to do. So a lot of times scientists never actually get to see what they're looking for. It's somebody farther down the road that actually makes the discovery. We build on past knowledge. If you want to go and look at this, there is a BrainPop, and there is a link here to it if you want to look at BrainPop's atomic model. This is like looking at a cartoon strip with a magnifying glass, and it's a pretty famous painting by George Seurat, and it's called Sunday Afternoon on the Isle of La Grande Jatte, and right now it's at the Art Institute of Chicago. And what you need to realize is this picture that you're seeing as a whole is actually pointillism. It is made up of individual tiny dots. And if we look at one of the gentleman's faces right here, you can actually see that his face that looks like a whole structure is a bunch of series of different individual dots. And if you look at that even closer, you can see the pigmentation above it. This is above the dog, and this is the paint dots on the canvas. So this is really looking at the fact that when we look at anything, what we perceive it as solid, in this case as an image, is made up of tiny dots. And how does that relate to atoms, you're wondering? Well, it's because we're all made up of individual teeny tiny dots. And the really cool thing is the electron clouds actually don't really touch each other. They're repelled. And so all of these little repulsive electrons, not wanting to get that close together, do actually come together to form molecules and compounds, which forms us. Isn't that cool? From the video, you know that all of our atoms are anything that's a heavier element than carbon. Basically, you have to have a star explode to have fused those atoms together into the heavy elements. We literally are the product of a star exploding. So you're all stars. Isn't that cool? But we're all made up of individual parts that make our whole. So Dalton, this dude, he had an idea of what the atom was. And he said, all elements are composed of atoms that cannot be divided. All atoms of the same element are exactly alike and have the same mass. Atoms of different elements have different masses. Well, that's true. Gold is much more dense than helium. If I usually have a platinum ring, and usually I'll let the kids try it, but right now I just have my white gold ring on. And platinum is noticeably heavier than you would expect it to be because it's a very dense atom. An atom of one element cannot be changed into an atom of a different element. Atoms cannot be created or destroyed in any chemical change, only rearranged. And that was where chemistry actually started. People were trying to make other metals into gold. The problem was you can't do it unless you literally break an atom down or fuse other atoms together to get the right amount of electrons. You can't make gold. Every compound is composed of atoms of different elements combined into a specific reaction. And then along comes Rutherford, and Rutherford's experiment is he shot a beam of particle through gold foil, and he expected it to go through, and some did, but some got scattered because it had to actually hit the nucleus to get refracted or bent into another direction. But what he found out is instead of it being solid, a lot of this stuff just went through. If you can't understand this very well, then stop mine, go into the notes, scroll down, and watch the video there, but I do expect you to have watched this video. Maybe.
In the early 1900s, Nobel Prize-winning British physicist Ernest Rutherford used alpha particles to discover the nucleus. Alpha particles are helium atoms with a +2 charge and are produced when uranium or other radioactive elements decay. Rutherford's team directed a beam of alpha particles at a thin gold foil. The alpha particle source consisted of a radioactive substance in a lead box. A small hole was cut into the box so the alpha particles would shoot out. Encircling the foil, except for a small slit for the alpha particles, was a strip of screen coated with zinc sulfide. As the alpha particles hit the zinc sulfide, a flash of light was produced. Until Rutherford's experiment, it was thought that the atom was composed of a sphere of positively charged matter with tiny negatively charged electrons embedded in it. The model for this theory was proposed by J.J. Thomson in the early 1900s and was called the plum pudding model. He reasoned that it was like pudding with raisins in it. If Thomson's model of the atom was correct, Rutherford's alpha particles would either go directly through the foil or be deflected very slightly. Remember, the alpha particles are large, energetic particles, while the electrons were thought to be very tiny particles, and the positive matter took up much more space than the electrons. Rutherford's team did see this behavior, but they also observed particles being deflected at large angles, with some particles deflected almost directly back to the source. On the basis of these results, Rutherford was able to come up with a new model for the atom. He reasoned that almost all of the mass of an atom is located in a very dense, very small center called the nucleus. He postulated that this nucleus contains all of the positive charge of an atom, and that most of the atom's volume is actually empty space with electrons traveling around the small nucleus. The researchers saw deflections at large angles, even straight back, because some of the alpha particles, which are positively charged, would come very close or even hit the positively charged nucleus and be deflected. Then, most of the particles went straight through because they encountered empty space. Rutherford's model is still accepted today, although scientists later discovered that the nucleus contains positively charged protons and neutral neutrons.
Okay, so here's another brain pop if you want to go and look at it, matter and chemistry and the atoms. You're welcome to. So let's start talking about compounds. So compounds exist in uncombined and combined form. Substances have to be made up of two or more elements into a specific ratios. For example, CO2, carbon dioxide, is 1 part carbon and 2 parts oxygen. A formula then is that combination of symbols that show a ratio of the element. In this case, H2O, 2 hydrogens, 1 oxygen, because there's no subscript, so it's implied there's only one, versus H2O2, as I said before, is hydrogen peroxide. So adding an extra oxygen on here, and it's not a very stable chemical, which is why it has to be transported in a opaque, that is dark color, brown bottle, so because it would react with light, and it breaks down into, guess what, water and oxygen. You don't want to drink it even if it's old though, so please don't ever do that. If you take a look here and want to go back and look at this, this is a chemical reaction. It's the epibirds, and they are actually going through with diacoke and mentose, and we know from the nucleation sites that diacoke and mentose have a chemical reaction releasing all the gas inside, and you can get some pretty cool things happening. If you want to watch it, go ahead and watch it. Here's some more. This is hydrogen peroxide and blood, which is why you really shouldn't do that. Okay, so a chemical combination, from changing one thing to another to a chemical compound, has a specific set of ratios, where a mixture, like a field of wildflowers, has no set, mixture. If I look at one flower section of a field, like a square yard or square meter, because we're science, and then go to another one, I'm not going to get exactly the same flower count of one type from every square meter to another square meter. So a mixture is, most matter actually does occur in a mixture. And a mixture is made up of two or more elements, compounds, or both. They're together in the same place, but they're not actually chemically combined into a new substance. Water is rarely ever found in its pure form. There's always other things dissolved into it, like in the ocean, salt. So these are a mixture of different types of candy. A salad is a mixture. Even within the tomato, there's a mixture of seeds, the softer pulp, the harder pulp, the liquids. I mean, you get mixtures in all sorts of things. Again, if you want to go back and look more, here's a Brain Pop link. If you want to go watch that, go ahead. So let's take a look at the element box. The element box doesn't have, this doesn't look like a lot, but this tells me a ton of information. For example, in the element symbol AU, aurum, gold, and it comes from Latin, remember, so normally we try and take the first letter or two letters, sometimes three if they're man-made. There used to be one before they renamed it, and I loved it. It meant 111, which is ununununium, but they've renamed it something else since then. I can't remember what 111 is, but I can look it up. So in this case, here at the top, usually what we do is, and this is usually this is a whole number. This is my atomic number. And it tells me how many protons are in the nucleus of gold. There's 79 positive protons. Now remember, there's two things that make up the mass. Well, you wouldn't remember this, but maybe you do. But the positive protons and the neutral neutrons are the two things that make up the bulk of the mass of an atom. And an electron's mass is something like 1/2000th of a proton. So we don't really even bother counting it. It's really the protons and the neutrons that make up the mass, and that's what this bottom number is. And you're saying, well, how can it be a partial? How can you have a partial neutron or proton? Well, because there's these things called isotopes, and like an isotope of uranium or carbon-12 or carbon-14, those are isotopes. In other words, carbon-14 has two more neutral neutrons than carbon-12, but they both have the exact same amount of protons, which is 6. So one has 6 neutral neutrons and one has 8, which is how, guess what? If I take the amount of protons plus the amount of neutrons, I get this. So my atomic mass. So if I take my atomic mass, subtract my atomic number, and if I know my atomic number is the number of protons, mass minus atomic number tells me how many neutrons are in the nucleus. So in the element symbol, we've got our atomic number, how many positive protons there are, which, by the way, usually if it's balanced, positive protons and negative electrons should equal each other out. We can get into places where it doesn't, but that's the general rule for figuring out what it should be. Then you've got your element symbol AU that tells me what it is. It's the abbreviation for gold. And then we've got our atomic mass. So on a piece of paper, I would normally have you fill this in. So let's look at this, and I would have you label this, and you're going to have a quiz on it. So pay attention because it's coming up shortly. You're going to have to practice it. Label each item on this element box of the periodic table. The top, this is the atomic number. The atomic number is 2. Helium, He, is its element name. And down here at the bottom, 4.00, it's the atomic mass. Now, it's important to understand that the number of protons is equal to the atomic number. So in this case, there's 2 positive protons. If I want to balance my charge out to 0, if I have 2 positive protons, I therefore have to have 2 negative electrons. So the interesting thing is the atomic numbers tells us the number of protons and the number of electrons. So how do I figure out the number of neutrons, you say? Well, I use this handy dandy atomic mass. This is the total of all the protons and neutrons together. So if I take away the protons, I'm left with the neutrons. So atomic mass minus atomic number gives me the number of neutrons. So then we go ahead and fill in this table. Here is a periodic table. In this case, carbon is 6. Its atomic number is 6. Its element symbol is C. Its name is carbon. And its average mass between all its isotopes is 12.01. Nitrogen is N. Its atomic number is 7. Its atomic mass is 14. Neon, atomic number is 10. Atomic mass is 20.18. Its elemental symbol is Ne. Remember, everything in a vertical column is called a group or family. And these things have strong relationships. These are all noble gases. This first column here, these are explosive metals. The farther down you get, they are explosive, but the farther down you are, the bigger they are, and the bigger the reaction. They're crazy explosive. And then we get into some other stuff. We're going to talk about that with periodic table, but we're really just looking how to identify a box. So in this case, zinc, Zn, atomic number 30, atomic mass 65.36. And we're going to need to use this periodic table. So I have one here and one below. You can use whichever one makes the most sense to you. So I want to figure out what each of these are. In this case, hydrogen. So what's the elemental symbol for hydrogen? Well, I go up here and find my hydrogen, and it's H. Its atomic number is 1, and its atomic mass is 1.01. So this is the only atom that doesn't have a neutron. So element symbol is H, atomic number is 1, number of neutrons, 0, none, nothing. Hg is right here. It's mercury. Its atomic number is 80. Its atomic mass is 200. So 200 minus 80 means there's 120 neutrons. So that's how you figure that out. And if you want to try it yourself, try a couple of these, go through and look for atomic number 29. By the way, these are numbered straight across 1, and they're numbered by periods, and there are 7 periods, 1, 2, 3, 4, 5, 6, 7. And there is trends that happen here, but we are numbered as they get bigger. So the atomic number gets bigger, the periodic table, it goes in that order. And then we group them where we restart by similar traits. So 1, 2, 3, 4, 5, 6, all the way through 10. So if I'm trying to find 29, it's right here. It's copper, Cu. Atomic number 29, mass 63. If I subtract that and round, so if it's 63, go to 63.55 would be 64. Subtract that from 29 and you get your answer. I don't know that I rounded up on here. I might have truncated. So this is the answer key to that one. Here's another periodic table if this one's easier for you to read. And right here and right here, they're different ones, but I gave you 2 choices for interactive periodic tables. So if I clicked on that, I'm guessing you lost that, so I forgot. I can't show you a different tab when I'm doing this. But if you click on that, you can see another interactive table. It's kind of cool. So your job today is to make sure you put in here that you've watched the notes. When you are done with this set of notes, you've finished the video, which is not yet, you are going to go to the rest of the items for today, which we're on day 2. and I don't have it written down here yet, but it is in here. You're going to go ahead, we're doing this the notes, then you're going to go and practice that element box quiz, which I may take the word quiz off. It's really just a practice. Here's your the practice of what we're going to do. In fact, I'm going to tell you it's not a quiz, but I'm telling you that it's a quiz in the fact that this will be on the test, so you need to make sure you know how to do it. So ask questions if you need help. So you're going to do that next. Then when you're done with that, you're going to start working on the 2 packets. 10, what are the parts of the atom, and what are elements? So your job today, finish the notes, which we're just about done. Go practice this element box like we went through in the notes, and then start working on your packets. If you have questions, as always, ask me in class, jump on Zoom, whichever way you're seeing me, that's how you're going to find help. Have a great day.